Back in ancient Greece, it was somewhat expected that if you were going to be a big philosopher, you were also going to be a student of the natural sciences. Therefore, you see a lot of big names like Aristotle and Archimedes, who are known for their philosophy, but also credited for various scientific discoveries such as buoyancy. Then, much later, in the mid-1500s to 1600s, we had big names Galileo of Galilei and Johannes Kepler, who gave us much of our foundational knowledge of astronomy and of orbital motion of planets. Also in the late 1600s, 1670s, we had this guy, Isaac Newton, who invented calculus because the maths of the time weren't good enough to explain the physics that he was observing. That, along with the studies of James Maxwell in the mid-1800s, are our foundation of what we consider classical physics. And for most purposes, classical physics is good enough. So we're going to come back to that in a second. But first, it's worth talking about some modern physics. Classical physics is generally pretty good so long as we're looking at things that we can see or imagine the size of, imagine the speed of. But if we're going really small, we need to look at quantum mechanics. Quantum mechanics exploded in the early 1900s with scientists such as Max Planck, who won the Nobel Prize in 1918 for finding the quantized energy, Werner Heisenberg for his principle in 1927, that is, the Heisenberg uncertainty principle, and other major physicists such as Pauli, Dirac, and Schrodinger, who contributed to the field. We have scientists Enrico Fermi, who got the Nobel Prize in 1938 for his contributions to nuclear physics, and Richard Feynman, who is really the person you should look to for any information if you want to talk about subatomic particles and their interactions. On the far other end of the spectrum, we have relativistic physics. This is the work mostly done by Albert Einstein. And as quantum physics are things too small to imagine easily, relativity mostly applies to things moving either too fast to imagine or are too big to imagine. Just as a concept, I have a sense of how big buildings are. I even have a sense of how big a mountain is. But when you actually say how big a state is in terms of looking at it, I don't really have any clue. I think of it in terms of how long it takes to cross instead of just size. Similarly, I can just barely imagine how fast a bullet is. I can imagine that if I shoot something, there's going to be a small delay before I see it hit the target. But I can't imagine how fast the light coming from lightning to my eyes is. I can't even really imagine the speed of sound, and that's pretty close to bullet speed. So when you're getting into that kind of speed or size, you need to look at relativistic physics. Basically, the faster you move, the slower time goes, and also the bigger you are, the slower time goes. We're not going to get into it too much, we don't have time for it. So, before we get back into classical physics, there's one other major branch of physics that's worth mentioning. That's thermodynamics. Thermodynamics has its own special little role because it isn't affected by modern physics acting on Newtonian physics like quantum or relativity is. It really just exists in its own world. And it's the thing that drives interactions between chemical bonds, nuclear physics. In many ways, it is the driving force behind anything that uses energy or creates bonds. In that way, we have three big rules for thermodynamics. One, across a large enough system, even if that system means the entire universe, energy needs to be conserved. You need to be able to track where energy comes from and where it goes, and it's never going to just appear or disappear. It always goes somewhere. Second, the universe absolutely loves chaos. In physics terms, it's called entropy. And basically, when I want to make a lot of small things become ordered or into one big cluster, I'm going to have to put energy into that to make it happen. And so that energy has a heat expenditure, which is going to cause more randomness elsewhere through extra motion and what have you. Meanwhile, I can also gain energy by breaking something apart, but the extra chaos of that breaking apart is also going to increase the total randomness of the universe. The universe is constantly getting a little bit more random. It makes sense. All it takes for a room to get messy is for you not to do anything about it. But for you to actually organize a room, you have to put effort in. The world tends towards chaos. And finally, there's always a cost towards putting that order in. I consider this to be the heat sink. Any time that you're doing work, there's going to be some inefficiency, friction, noise, whatever. You can't have a perfectly perfect system, a perfectly efficient system. There's always going to be that heat tax. And also, on its own, energy is going to tend from hot towards cold. Without putting in a lot of extra energy, there's no way to drive the reaction the other way for free. That's sometimes referred to as Maxwell's demon. So, speaking of Maxwell, we get back into classical physics with James Maxwell, who did his work on electronics. There's only a couple really big takeaways that matter for basic physics purposes. One, that if I have an electron, which therefore has a negative charge, nuclei, by the way, protons, have positive charge, and if I move it through an electric field, it's going to accelerate in the direction of the electric field. If I have a charged particle and I move it through a magnetic field, it's going to curve. Meanwhile, anytime I'm accelerating a charged particle, as with curving it, it's going to create an opposing magnetic field. Similarly, by accelerating a magnet, you can do this very easily. Take your bar magnet and move it, that is literally accelerating a magnetic field, and that's going to create an opposing electric field. They're tied in together. And then, if you want to get this quantum, there's several equations called the Maxwell-Bloch equations. And that's just taking the old Maxwell equations and making them quantum. And now, finally, we return to Newton and Newtonian physics, also referred to as classical mechanics. Mechanics because it describes how the world works when things are interacting with each other or in motion. So, on that note, Newton has 3 laws of motion. You're probably at least a little bit familiar with them. First, that an object in motion will stay in motion, and an object at rest will stay at rest, unless acted on by an outside force. It's really very simple to think about. If you imagine having a ball rolling across the field, it's going to keep rolling until friction slows it down or it bumps into something. On the other hand, if you kick it, it's going to change direction. That's an external force. Also, a ball just sitting on the ground is going to sit there forever, unless suddenly the ground becomes a hill, or once again, you kick it. The second rule is that the acceleration of an object is equal to the force divided by the mass of the object, more often written as force equals mass times acceleration. Very simply put, again, you have an object, and the heavier it is, the harder it is going to be to make it accelerate, and the harder you push on something, the more it's going to accelerate. Finally, we have third rule of motion. Finally, we have the third rule of motion, possibly the most well-known, that for every action, there's an equal and opposite reaction. This is the momentum problem, that for me to push something this way, I need to have an equal force pushing the opposite way. Very simple. For Newtonian physics, we use velocity, not just speed, and it's the derivative of an object's position. If you want to recap on derivatives, I have a short video linked below. But, getting back to it, we can also see that acceleration is the derivative of the velocity, and not that people usually go beyond that, but the derivative of acceleration is called jerk, and we can keep going to snap, crackle, and pop. Yeah, physicists think they're cute. Finally, we also have what happens in Newtonian physics in a collision. There's two major types of collision that we generally like to use because they're simplified. That's either wholly elastic collisions or wholly inelastic collisions. In an elastic collision, the two objects are going to hit each other and then bounce back without losing any energy. Meanwhile, in a wholly inelastic collision, the two objects are going to hit together and then they're going to stick, maintaining their momentum whichever direction is bigger. Now, regardless of whether it's elastic or inelastic, you have to keep momentum constant. That's one of the big rules of physics. So, that's one equation that you can use to see what happens in the collision. In an elastic collision, you also know that energy is conserved. That is, kinetic energy is conserved. That gives you a second equation, which often makes it very simple to solve exactly what happens after the collision. In mathematical terms, the momentum of an object is simply its mass times its velocity. There is a directional component to that, so make sure that you keep that in mind whenever you're doing some equation. Meanwhile, the kinetic energy of an object is equal to 1/2, once again, times the mass, but this time times the velocity squared. Just a few more useful Newtonian equations. We can define work as a change in an object's energy, which is going to be equal to the external force applied in the direction of the object's motion over whatever distance the object moves. If you happen to know what the velocity and acceleration are over that distance, which, if you know the force and the mass, you should be able to calculate, you can change that over the distance moved with over the time in which the object is moving. That's often easier. Also, when moving through a field, the potential energy is going to be equal to some force constant relative to the field, the charge or quantity of the object that is being worked. So for electrical fields, that's going to be the charge. For something like gravity, that's going to be your mass. And then times the distance once again moved. A simple example, if I push a boulder up a hill, then the force, once again, is going to be the force of gravity near Earth. That's 9.8 meters per second squared. The quantity is the mass of that boulder. And the distance, we have to be a little bit careful in because it's going to be the distance opposing the field. So that's the distance that the boulder moves up, not the distance along the hill. In my opinion, there's two field strength equations that are worth memorizing by heart: gravitation and the electrostatic force. Gravitation, or simply gravity, is going to have a force equal to the gravitational constant, which is easy enough to look up, times the product of the two masses divided by the distance between them squared. Similarly, the electrostatic force is going to be equal to Coulomb's constant, again, look it up, times the product of charges divided by distance squared. Finally, also, it's worth knowing the potential energy of springs, which is just going to be so-called 1/2 kx squared. Yes, it looks very similar to kinetic energy. And in this case, k is just some constant which refers to the strength of the spring. So, in summary, that's all of physics. Well, kind of all of physics. Well, kind of a very small portion of a very small portion of abridged physics. But at least we got some of the big words and some of the big names. Is there something critical which you think I missed? Is there something that I just explained wrong? I'm willing to bet there is. It's a big field, and even though I do consider myself something of a physicist, I have a minor in it, it's been a while, and it's a complicated field. Let me know in comments below, and if you enjoyed the video, like, subscribe, and don't forget to click that notification bell so you never miss out. Until next time, see ya.